Hello everyone. In this video, we discuss logistic regression and loss functions for classification problems. This lecture is designed to be more focused on theoretical aspects of classification problems. And in the next lecture, we're going to shift our focus to more practical aspects of classification problems, including how to properly evaluate them. Logistic regression is a powerful statistical method used to model the probability of a certain event or outcome. Recall that in a classification problem, we have events, outcomes, or labels that they are discrete or qualitative. And in this case, it's particularly useful for classification problems where you want to predict if something belongs to a specific category or not. If we want to mathematically represent this, we can write this as a probabilistic model where we want to find the probability of the label given the input. So this x is the input vector. And throughout this course, we assume that if we have a tabular data set, this x is a d-dimensional vector where each element of this is one feature that we're going to use as inputs. And this theta here is what we use to represent the unknowns of our model. Something I like to emphasize is that throughout the course, sometimes we use W, sometimes we use theta, depending on the context. But what really matters is that all of these are basically containers for the unknowns that we have to find for our model to work properly. So the naming doesn't really matter as much, but what we are trying to say here is that we want to, for each input X, we want to find the probability that the label for that input belongs to one of the classes that we have. And of course, we have to find these unknown parameters. Something else I'd like to emphasize is that when we talk about logistic regression, by default, we mean usually binary logistic regression. And in this case, we assume that these outputs are either 0 or 1. And this comes very much from, for example, saying that one corresponds to success, the other one corresponds to failure, or one class corresponds to yes, the other class corresponds to no. And this is a very common type of classification problem that we encounter in many real-world problems. However, we can generalize these to cases where we have more than two classes. And this is something usually known as multinomial or multi-class logistic regression. And in this case, it is typical to label these classes or categories as 1, 2 through C. And in both cases, what's really important to know that these values that we use here, these numbers, they do not have any quantitative value, right? So these are just to let us know that we have two different categories. So we can label these as -1 and 1 or 0 and 1. And in this case that we have multiple classes, if we really want to be consistent with the binary case, we can label these 0, 1 through C minus 1, which means that still we have C different categories. So throughout classification problems, these labels do not matter as much as it shows that we have distinct categories and groups, and they do not have any quantitative values. And this is exactly why we cannot use the same loss function as regression problems that we saw last time. Because in this case, we cannot just simply subtract outputs and raise them to the power of 2, like what we do in mean squared error. Because in this case, these labels do not have any quantitative values, and we have to find something that can take into consideration that in this case, we have these probabilities of each data point belongs to one of the classes that we have. So for now, let's start focusing on the simplest case, which is the binary logistic regression, where we have two outputs, 0 and 1. And this should remind you of something that you have seen before in probability, which is known as the Bernoulli distribution. So what is the Bernoulli distribution? It's a discrete probability distribution representing the outcome of a single binary experiment, where the result is either a success, which we usually represent that by 1, and this happens with probability theta, or it's a failure, which represent this by 0, and that happens with probability 1 minus theta. And the reason for that, of course, is that because we have two outcomes, the sum of probabilities must equal 1. So in this case, we only need to define the probability of success, and that will automatically tell us the probability of failure, because the sum of these two probabilities must equal 1. So you immediately see a connection here, right? So we said that in the binary logistic regression, we have two outcomes. And in a Bernoulli distribution, we also have two outcomes. And what we really need to properly define this distribution is providing this probability of having a success, which is 1. So to make this a little bit more formal, we can look at the probability mass function, or PMF, of a Bernoulli distribution. And I use this BER for Bernoulli distribution of this variable given this parameter theta, because we need that. And if y equals 1, that's theta. If y equals 0, is 1 minus theta. Something to keep in mind is that we can actually write this in a more compact form, using the fact that these y's here are either 0 or 1s. And we can write this as theta raised to the power of y, 1 minus theta raised to the power of 1 minus y. And why does this work? So if y equals 1, this exponent is 1, and this exponent is 0. So it means that this first term is only active, which is theta, and that's what we want. And if y equals 0, then 1 minus 0 is 1. So this exponent is 1. And the first exponent is 0, which means that the only term that is active here is 1 minus theta. And that's exactly what we have here in these two conditions, right? So this means that the probability mass function for Bernoulli distribution can be indeed written in this form. And putting everything together, this means that for binary logistic regression, that we are looking for this probability of a data point belonging to one of the two classes, we can write this as a Bernoulli distribution. The only thing that we have to find here, what is that theta parameter that determines the probabilities of success and failure? And that appears to be a function of the input x and some unknowns applied to this function, which is sigmoid or logistic function. So a very crucial part of this lecture is to understand what this magical function is. So for now, to get started, let's look at the definition of this sigmoid or logistic function. And throughout this lecture, I sometimes say sigmoid, sometimes say logistic. They're obviously the same thing in this context, and I use them interchangeably. So the formula for the sigmoid function is 1 over 1 plus e to the negative a. So we can mathematically, using the tools from calculus, analyze the behavior of this function, finding asymptotes, etc. But since this is also a course we are using a lot of programming tools, let's visualize this function to see what it does. So we have to provide some values for this input a, and then put it into this function and see what the outputs are, right? And that's exactly what we do here. Let's say we want to plot this from -10 to 10, and we choose 100 equally spaced points. You can change these lower and upper limits to anything you want, from, for example, -100 to 100 or -5 to 5, and then you define your function, and we plot x versus y values. And the rest of things here are just for customization to make sure we properly label x and y axis, etc. So here it is. This is our sigmoid or logistic function. And something I want you to pay attention to is that the input to this function obviously is a real valued number here from -10 to 10. But something which is very interesting is that the output, it looks like it's always from 0 to 1. And this is not by coincidence, because what we wanted to do here was to make sure that this is a valid value for theta for the Bernoulli distribution. And we know that because this has this interpretation that this is a probability score, this must be always between 0 and 1, otherwise we get into trouble. So therefore, this sigmoid or logistic function is a way to ensure that we always get something that is from 0 to 1. So to go back again to what we have here, this means that first we find a function of the input and these unknowns. And whatever this thing is, this is a real valued number. We can pass this through the sigmoid function and we get something that is from 0 to 1. And that's definitely a valid theta for the Bernoulli distribution. So this sigmoid function or logistic function has a lot of nice properties because you can think of multiple ways of getting some real value numbers and mapping them to 0 to 1 to this interval to be a valid probability score. But there are definitely other considerations here. And one of these things is that this sigmoid or logistic function has this very nice closed form expression for its derivative. To derive these, let's look at our notes here. So the logistic function is 1 over 1 plus e to the negative a. And if you want to take the derivative of these, probably the easiest way is to write this as 1 plus e to the negative a raised to the power of negative 1. And now if you take the derivative, you can obviously use the chain rule and call what we have inside these parentheses as z or something else, give it a different name. But we can do this probably even faster. And we know that if we consider this as, let's say, some variable, then we get negative 1, this variable raised to the power of negative 2, and then we have to find the derivative of what's inside these parentheses. And if we simplify this, and if we use the fact that we know that the derivative of the exponential function, we can see that for this last term that we have here, so derivative of 1 is 0, and then we get this negative sign and negative e to the negative a. And something that you need to do at the end is to also decompose this into two terms, right? So we have this 1 plus e to the negative a, which is in the denominator, and we have this power 2. So we can write this as 1 plus e to the negative a times 1 plus e to the negative a. And we only have 1 e to the negative a in the numerator. So it is very easy to see that this first term is exactly the sigmoid or logistic function. And you can easily show that the second term is actually 1 minus sigmoid of a. And therefore, the derivative of the sigmoid function is the sigmoid function itself times 1 minus the sigmoid function. And you will see later on that this property is crucial for classification problems to have nice loss functions or cost functions. For now, let's just make sure that we did the math correctly. That's again the nice thing since we can use here Python. So again, we are going to define these a's from negative 10 to 10. We have the sigmoid function, and then we plot this. Also, we plot the derivative, right, which is sigmoid times 1 minus sigmoid. So here we can look at this function and its derivative. So it is very clear for the negative values of a, we start from derivatives that are very close to 0. Then the derivative that we have here increases to reach its peak at 0.25. And then again, it goes to 0, which is consistent with the fact that we have these two horizontal asymptotes, one at 0 and the other one at 1. And if you want to know, for example, what happens exactly at 0, so you can see that if a equals 0, the sigmoid function is 1 over 2, so it's 0.5. So then the derivative at that point is 0.5 times 1 minus 0.5, which again is 0.5. And this gives us 0.25. And that's how we get this maximum value. So of course, we can do more mathematical analysis on this function, but I think this plot that we have here says a lot about the behavior of this function. But let's get back to our binary classification problem now that we know more about this special sigmoid or logistic function. So what this means is that the probability that the label is equal to 1 for a data point is this sigmoid function, because this is that parameter theta of the Bernoulli distribution. And that's 1 over 1 plus e to the negative a. And we can multiply both numerator and denominator by e to the a, and simplify it, right? So we get e to the a in the numerator, and 1 plus e to the a in the denominator. And similarly for probability of y equals 0, the way that you can always think about this is 1 minus the other probability, the probability that y equals 1. So that's 1 minus sigmoid of a. And this is what we have. And again, you can multiply this by e to the a, and you get this formula here. And here, interestingly, what we think we can do, so let me show you this in our notes. That might be a little bit easier to follow. So we have these two probabilities. Now you can divide the probability of y equals 1 by probability of y equals 0. And you can see that these two terms cancel, and you get e to the a. And now if you take the logarithm of both sides, you get to this point that log of probability of y equals 1 over y equals 0 is equal to a, which is very interesting, right? Because the way you can think about this is, summarized here, right? So you have this a, which is a real valued number. You give this to the sigmoid or logistic function. This gives you a probability score, right? That was the property of the sigmoid where the output is from 0 to 1. So if you provide this a, you get this probability. But something that is also important if you want to make sure that we have a well-defined problem is that if you know the probability, you should also be able to know what value of a led to that probability. And that's exactly why this analysis here is important, because it's telling us that if you find the log of probability of y equals 1 over probability of y equals 0, that's the a value that we are looking for. So in other sense, this function that we have here, which we call it the logit function, is able to get this probability score and tell us what this value of the a is. So it's a two-way process, right? So you have this sigmoid or logistic function that provides probability scores. And then if you provide probability scores to the logit function, then you get the real valued numbers that we had here before applying logistic regression or logistic function. So we have this here summarized in terms of like the main steps. That's the logarithm function that gives us a, and therefore the inverse of the sigmoid function is called the logit function. And here is the formula, p over 1 minus p, because we have always probability of y equals 0. So let's look at this and make sure that this makes sense. So we import numpy as np. Also, both the logistic function and the logit functions are already implemented in SciPy, which is another important scientific computing library in Python. And inside SciPy, we have a module called a special. Now we know how this works, this dot notation. So we have the package, and then we have the module, and then we import this to logistic function and the logit function. And what we do is that in this case, instead of working from -10 to 10, I'm working from -5 to 5. And we can give these x values to the logistic function. So this is exactly what we implemented from scratch before, but now we are just using this built-in function. And then for the logit function, remember the input of a logit function is always from 0 to 1 because it should be a probability score. And now we can look at the output of this function. So if you plot this, you can see that logistic function is exactly like what we had before. And always let's check things at like 0, right? So if we have input 0, the probability that we get is 0.5, exactly here. And now for logit function is the inverse of the logistic function. And if you provide 0.5 as the input, then we get back 0, right? And that's exactly what we expected, because this is telling us if we want to get probability 0.5 after applying logistic function, the input to the logistic function should be actually 0, right? And that's something exactly we see here. And therefore, the nice thing is that whenever you're working with these types of classification models where they utilize logistic function, because we're going to use this later on in neural networks too, this is not just applicable to logistic regression, then you can see that the fact that we have this inverse function is extremely helpful. And just to right now to complete our discussion about logistic regression to understand what this statistical model is, we have a linear function of the input inside the sigmoid function, right? So before we had this sigmoid logistic function and then another function of x inside. But since this is a linear model, and we have seen this in a linear regression too, what we do is we make this linear assumption that the way that we transform the data is just simply represented by dot product or inner product. And you can see here the connection with some of the stuff we're going to cover later on. One thing we can do to improve logistic regression in terms of being able to distinguish between different classes is obviously having more complex data transformations, which takes us back to this diagram we had from lecture 1. And I said that this is very important because right now we can think about it in this way, that in the very classic logistic regression, you do one data transformation, which is this dot product or inner product, and then you pass this to the sigmoid or logistic function. And now if you have a very advanced neural network model that is supposed to classify some images or something like that, then we may have multiple layers of data transformation, but it is still a very similar idea that we're going to need to use the sigmoid function to make sure that we have probability scores. And then also we need to make sure that we have appropriate loss or cost functions. Since here we are working with probability scores, we cannot simply subtract true versus expected outputs, because if we do that, everything's from 0 to 1, and we totally lose the interpretation of these outputs that are probability scores. But for now, we know basically logistic regression, where we have this linear transformation, and therefore probability of y equals 1 given inputs and these parameters is 1 over 1 plus e to the negative a, and a right now is this dot product between w and x. So we have defined the model that we have for logistic regression. The only thing that is remaining here is that what should be this loss function or cost function to make sure that we can find the optimal value of W, so that we match this model to the data set that we have. And that's something we're going to cover in the second part of this lecture.